Um,
Good morning, everybody.
oh wait.
Okay.
Yeah. Yep.
Good morning to Wag. Good morning, everybody. Sorry. Today I will talk about arsenic problem and mitigation strategies in Bangladesh. Before that, I would like to introduce myself. I am MD Anaduzzaman Kazul from very northern part, the city called Rajshahi from Bangladesh. I completed my bachelor in civil engineering in 2009 from Rajshahi University of Engineering and Technology, which is situated in my home city. And then, after my bachelor in engineering, I moved to Stockholm, Sweden in 2010 for a master's in environmental engineering and sustainable development from KT's Royal Institute of Technology. After completing my master's in 2012, immediately I started my licentiate engineering degree, which was research-based MPhil study, and finished in 2015 from the same university. And then I moved to more northern part of Sweden called Luleå University of Technology, where the temperature is minus 41 degrees, as a research engineer. And in 2016, I moved to TU Delft to conduct my PhD. So since 2011, I'm working on arsenic-related problem and mitigation aspects, especially in developing countries like Bangladesh and India. Current research mostly focused in Bangladesh. So let's talk about arsenic and perspective to its mitigation in Bangladesh. The geogenic occurrence of arsenic in shallow depth groundwater is a severe drinking water quality problem all over the world, where groundwater is used for drinking purposes. Unfortunately, the discovery of arsenic and their widespread occurrence in shallow aquifers drastically reduce the safe water access, and a huge population is exposed to high level of arsenic from drinking water sources. The major arsenic-related health outcomes are different types of cancer, childhood intellectual health, cardiovascular disease, skin cancer, or something else. Consequently, over a million to 200 million of people worldwide are exposed to arsenic-contaminated water. This problem is more extreme in Southeast Asia, especially in Bangladesh and West Bengal, India, as you can see here. So, like other countries, Bangladesh is also a country where groundwater is extracted for drinking water purposes, and Bangladesh people, more than 90% people, depend on groundwater. Consequently, millions of cell tube wells has been installed to extract water for drinking purposes. Unlikely, arsenic contamination limits to availability of safe water, which has been detected first in 1993. Around 30 to 35 million people are exposed to arsenic level more than Bangladesh drinking water standard of 50 microgram, where World Health Organization suggested 10 microgram per liter allowable limit. So it is important to provide arsenic safe water by means of awareness building, screening, and provide through safe sources or treatment. If we talk about awareness building, in 2000, with the help of World Bank, UNICEF, and Department of Public Health Engineering, the People's Republic of Bangladesh, a large campaign carried out to screen more than 10 million wells to identify arsenic safe and contaminated wells, parallel to inform people related to arsenic problem and aware them not to use contaminated sources. During that campaign, they marked the wells as green to indicate that wells is safe to drink, that have less than 50 microgram per liter of arsenic in that well, so people are allowed to drink or use for cooking as well. And red mark in the wells as not safe for drinking and cooking. So usually now people are using these red mud tube wells for other purposes except drinking and cooking. These posters create huge awareness among rural communities in Bangladesh. If you talk about screening, because the told first need to identify the contaminated source so people can stop drinking from it. For this, screening is important. There are varieties of screening tools commercially available, like hack test kit, came in curve field test kit, rapid screening test kit, Arsenic, and so on. Most of the kit usually show the range of arsenic contamination level like this. However, these kits are depends on use of chemicals and it is time consuming. Around 20 minutes is needed per test. It also depends on skilled personnel, risks of health hazards, and especially costly to limit the availability to the uneducated and poor rural people. So it is important to find new identification tool that can be convenient and use of no chemicals and anybody can use. Based on this idea, the platform color tool can be one of the options. What is platform color tool? The concrete slab platform that used to protect the wells. This platform actually how it works during the extraction of groundwater. If the water is coming from the manganese oxyhydroxide reduced aquifer or sediment layer, then the water coming during the pumping water coming out, so manganese and arsenic in the water comes, and this arsenic is readily absorbed to the nearby iron oxyhydroxide surface of sand layer in the aquifer sediments, and manganese remains in the water. So manganese is coming out during pumping, and due to the oxidation, the manganese oxidized to manganese oxidized, manganese oxidized, and produce the black coloration on the platform. On the other hand, once the water is extracted from iron oxyhydroxide surface, the iron and the arsenic that was here, both of them are coming together during pumping. Iron oxidized to iron oxide and produce red colors. And this red colors means this water contains high arsenic. And this black is for manganese, as I said. So the difficulties is arsenic don't have any taste, color, or any significance. So you can't identify what is it. So based on the color that developed from other like manganese or iron, you have to identify this one. Then, if we talk about alternate option to supply arsenic safe water, then immediately two options comes in mind. One is alternate safe source, or number two, treatment and supply to the of contaminated water. So what could be the alternate source? Shallow tube wells that is less than 70 meter in depth. That is, as I said, it's usually contaminated with arsenic. Intermediate deep tube wells that is 70 to 150 meter in depth, or deep tube wells that is 150 meter or above. So intermediate deep tube wells has low arsenic but high manganese problem, and deep tube wells usually no arsenic but low sometimes, or surface water as there is no arsenic problem. So if we talk about the tube wells, then it is important to identify the arsenic safe aquifer to extract the groundwater during installation. So based on that, the sediment color tool has been developed that can be used during installing the tube well. Like you see, once you are installing your wells and if the well is screened, if it is in black sediment or black sand layer, then there is high risk of arsenic because it's highly reduced. And if you go from left to right, then you can see the red color sand level. So if you extract the water from red color layer, of the sand, then you'll have low arsenic. So you can use this tool, and this tool, based on this color idea of sediment or sand, this tool has been developed. So it will help the driller, who usually the responsible person to install the wells in individual person. So they can identify and they can select the layer of the screen to extract water. So if I talk about altogether, then the shallow wells, it is, I said already, arsenic contaminated more than 50 microgram. Intermediate oils have manganese problem and 5 times expensive than shallow tube oils. Deep tube oils, it's 10 to 15 times expensive than shallow tube oils. So it is not possible for poor rural people to install these expensive oils. If you talk about surface water, that's a good option, but there's high risk of fecal contamination. And unfortunately, like many developing countries, there is no regulation to maintain water quality, the surface water body. So the next mitigation measures can be treatment of contaminated water. Different treatment options or alternate option has been tried out, like the arsenic safety valve that I discussed already, ponds and filter, where arsenic contaminated water is extracted and flooded the closed water body, like this one, the concrete water body, with sand in it. And by using tap, they can have arsenic safe water. But due to improper maintenance and negligence, water can easily be contaminated with bacterial contamination, along with it has taste problem that people don't like. And also sometimes aesthetic context people don't like to have. Sometimes it is open. Then rainwater harvesting. It could be a good option, but it is seasonal solution. Only during rainy season you can use this one as an option for water supply, which is which can be used only during rainy season. However, it also has risk of contamination, and people don't like the taste of rainwater as there is no proper mineral composition. So arsenic removal filter. It will only work if it is central system for educated people with household filter. But the complexity of the filters make it difficult to be sustainable. It needs sophisticated uh, maintenance, like need to change absorbent hazardous waste produces and need proper disposal. And it demands regular maintenance and also need skilled manpower, and ultimately it's quite costly for the rural people. Based on the different alternate options that have been provided, if we talk about the abundance rate of these things, then if you go from the bottom, arsenic removal filter, almost 100% of the supplied system or different options is not working. Filter that used to remove bacteria from arsenic surface water, like Vishuddha filter they called it, that is also not working, 100% failure, because they tried for more than 10 years and everything is failure. Ponds and filter, still it's failing because like only, let's say, 10 to 12% is working. Rainwater harvesting is not also working, more than 50% is failure because it only can use during rainy season. Only arsenic safety valve is possible because it's need low maintenance and uh, easy to operate. But the thing is quite costly for the people. So, among available treatment options, arsenic core removal with iron that comes from same sources may be the ultimate option as no further adsorbent is needed. Where during the oxidation state of groundwater, iron oxidizes to iron 3 and form HFO flux, which act as a natural adsorbent for arsenic. However, core removal is hampered by naturally uncharged arsenite, usually present in anoxic groundwater. So because treatment option mainly work for negatively charged form, so it's quite easy as a positive negative binding form, but it is don't have any charge, so that's not possible. To solve this problem, usually different type of oxidant used during the treatment option, like hydrogen peroxide, potassium permanganate, sodium hypochlorite, manganese oxide, or ozone, and others as well. So how it's work in rapid sand filter? Once you extracted the iron and arsenic-rich contaminated water in an overhead tank, then you're feeding to the sand filtration like this through the aeration. During this aeration step, iron is oxidized to iron oxyhydroxide, that is HFO flux. And the other hand, arsenic 3 oxidizes by arsenic oxidizing bacteria. That bacteria comes from groundwater itself, indigenous bacteria, and it's growing on the sand top layer over the time, and it helps to oxidize arsenic 3 to arsenic 5. So once iron oxyhydroxide is formed and arsenic is converted to arsenic 5, then they come together and make complexes, iron arsenic complexes, and removed by the sand layer. So based on this idea, we checked in a pilot study in the two form of before the column experiment. We stored the water in two form, like oxic condition. Before storing in the overhead tank, we make the aeration like the shower head, and another is anoxic condition without air supply, directly supplied to the bottom of the tank. Based on that, we found that the groundwater arsenic concentration was more than 300. In the tank water, some change happened, but in the filtrate in the column of sand filtration system, we found that once we stored the water in oxic condition and then further treated in the sand column, we have high level of arsenic in the filtrate that not uh, compare with the 50 microgram per liter of arsenic. But in anoxic system, it's compared with 50 microgram per liter. So anoxic system helping to remove our higher arsenic. Based on that concept, we have been piloted the water supply system in a small scale in the following way. The water is extracted from shallow arsenic contaminated wells and stored in an overhead tank, anoxic tank, and then fed to the column that contains plastic carrier to help oxidize iron that comes from groundwater and growth of bacteria which helps to arsenic oxidation. Then the filtrate from the plastic carrier column come to the sand filtration and removal happen of arsenic and iron on the top layer of sand column. And this filtrate comes through the resin column, because if all the arsenic is not removed, that oxidized already. So we use this resin column as a final barrier, so it will capture all the arsenic 5 and then finally came to the reservoir, supplying reservoir. Then people can extract from this point to drink. In real scenario, the pilot experiment is like this. So the overhead tank, then plastic carrier, then sand, then behind this one you have the resin column. So there is three setup to supply sufficient amount of water to the people. So if we come to the conclusion as a take-home message, we can say then that there is no single measures and need to check different alternatives based on the suitability. Awareness building is must along with suitable measures. So Bangladesh developing progressively related to arsenic problem need to find sustainable measures to screen like black from color. Arsenic safe option need to be based on locally available materials like rapid sand filter, because you are not using any chemicals and quite easy to operate and maintenance. So people only use quite frequently. So that's it. Thank you.